Hi, welcome back to another video. This video will be about the RISC-V 8 architecture. So a little bit of an introduction. RISC-V 8 is my project on building an 8-bit fully pipelined breadboard CPU, and this video will be about the architecture of it. So the architecture inspiration for my project was from the Patterson and Hennessy book called Computer Organization and Design RISC-V Edition. This is an image of the book cover. What is RISC? RISC stands for Reduced Instruction Set Computing, and it uses a reduced instruction set with a smaller number of simpler instructions in a load store format. This format is where it loads data from memory and then into registers and then computes the data in the registers and then stores the outcome back into memory. And it has simple hardware and uses pipelining, which leads to faster execution. But the downside of this is that it will need more instructions to do more complex things. What is RISC-V? RISC-V was introduced in 2015 by UC Berkeley and uses the RISC type architecture, and is used to simplify the CPU architecture. What is pipelining? Pipelining increases the speed of the clock cycle by letting each stage of the CPU work in parallel on different instructions. And each clock cycle, the goal is to have all instructions in each stage completed, which leads to one instruction completed per clock cycle. But while using pipelining, there can be hazards, which I'll talk about in a later part of this video. And I'm using pipelining because it's a bigger challenge and I want to learn how it works. So what are the 5 stages in the CPU architecture? So the 5 stages are fetch, which I'm going to be talking about first, decode, execute, memory access, and store. And I got all of these stages from the Hennessy and Patterson book, except I renamed right back to store. So the first part of the CPU I'm going to be talking about is the fetch stage. This is the PC. The PC is the program counter, and it has the instructions it has the address for the next instructions. So after each clock cycle, we will have to do PC plus 1 in this adder to get the instruction after the next one. We will also need to implement stalls in the PC and each of these registers, but I'll talk about that in a later part of this video. And sometimes if the branch is taken, then the new PC, instead of becoming PC plus 1, will be the address for it's the jump address. And it will find that out in the execute stage. And in order to remove the already used instructions, because this is a pipeline, we're going to have to bubble them out, which just removes them. Okay, now I'll talk about the decode. So the decode receives instructions from fetch and separates them into operators and operands for the execute stage. And this is the decode controller EEPROM, and it acts like a hash table. And based on the opcode it receives, this 5-bit opcode that also gets sent to execute, based on the opcode, it will activate a certain control signal based for one of these 4 types. And also the certain operand. So this PC plus 1 gets forwarded from here, from fetch all the way to exit, from the fetch decode register all the way to the decode execute register, and I'll talk about that in the execute stage. Also, this RD selector gets also forwarded, and I'll also talk about that in the execute stage. Okay, so this PCFD, if it's activated, then it's used for the JLR, and it's the jump address. If it gets activated, it gets sent to OP1. And this U type, if it gets enabled, it's an 8-bit immediate used for LUI, and if it gets activated, it will get sent all the way to OP2. If it activates the I type, then it's because it's a 5-bit immediate, we're gonna have to sign extend it before sending it to OP2, and the same for the SP type. If it's activated, it's gonna go to the sign extender and then send all the way to OP2. And instructions can also come from the register file, and if they do, then it gets forwarded straight to OP1 or OP2 for the execute stage. But if it that could cause hazards, which I'll talk about in the hazard logic. Now I will talk about the hazard logic. So if a hazard is detected, then the hazard logic will forward the register values from execute or memory access stage instead of reading from the register file. And I'll go over the logic for it. So if the RS1 selector for decode is reading while the RD selector for the execute memory access register is writing to that same register, then it will cause a hazard. And if the RS1 selector for decode is reading from the same register that the RD selector for decode execute is writing to, it also causes a hazard. And same for RS2 for both of those conditions. Okay, now I'll talk about the stall. So if the instruction in execute is a load word, only load word, then the RD value won't be available till the instruction gets to memory access. So the decode and fetch will have to stall until the instruction goes to memory access, and then the RD value will be available. So then after that, then you forward it. And then there's one more case, which is if the instruction's in store, which I'll explain in the store stage later on. Now I'm going to talk about the memory access stage. So first of all, data memory and instruction memory are two separate chips because I'm using Harvard architecture, and data memory will only be used for load and store instructions, and all the other instructions will come from this execute value, which will go straight to the RD value if it's not load or store. Okay, it's going to get the data for the data memory from this RS2 register and the address from this ALU value, and it's going to have control signals that read or write based on if they're activated or not. And it's just going to send it to the RD value for the store. Now I will talk about the store stage. The store stage gets the value that it's going to be storing from this register and stores it all the way back to this register file on the down edge of the clock. And it stores it on the down edge because it doesn't want to create a hazard, because the decode will be reading, and if it reads and writes at the same time, a hazard will happen. Okay, now I'm going to show you the diagrams that I used to build the model with. So we have the clock diagram, the fetch diagram, the register file, the branch comparator, the decode, which is the biggest one, the execute, and lastly the memory access. And all of these will be found on my GitHub